Example 4, it says a tailor has a piece of cloth in the shape of a right-angled triangle as shown below. The piece of cloth has a base length of 30 and a perpendicular height of 40, and the tailor wants to cut out a rectangle from this piece of cloth. The rectangle has a width W and a height H. And then all of a sudden part A says express H in terms of W. So H in terms of W means we've got to get an equation with just H and W in it, and we'll have to make H the subject. So how on earth do we set up an equation with H and W? Well, what you'll notice is that W is one of the sides of this big right angle triangle, and H is actually one of the sides of the smaller right angle triangle. So if we take a look, I've copied out the diagram. What you'll notice about these two triangles is that they are similar. Now, to cast your mind back, what makes triangles similar? Well, all their corresponding angles have to be the same. First of all, this triangle up here, that's clearly a right angle, and this little triangle down here, that's a right angle. So these two corresponding angles are the same. What you'll also find is that this angle here in the little triangle and the little angle here in the bigger triangle are also the same because they're corresponding. Remember, this line and this line are parallel, and there's the third line joining them, so you've got an upside down F, so you're using the F rule here. So that means those two angles are the same, so they're corresponding, which means then that this angle up here and this angle down here are also corresponding. Again, you're using the F rule because there's your third line. These are the two parallel lines, and the angles in between them correspond. So we have similar triangles. So I've copied the two triangles out that are similar. So I've put the big one down first, and I'm going to put some measurements on it. So we have W. Now this distance here is 40, subtract H. And then if we go to our other similar triangle, this distance here is H. And then this little distance here is 30 subtract W. Now, when two triangles are similar, that means the scale factor of enlargement for every pair of corresponding sides is the same. So for example, if I take these two corresponding sides, the scale factor of enlargement is the larger side over the smaller side. So for these two sides, the scale factor of enlargement would be 40 minus H all over H. Now that will also be equal to the scale factor of enlargement for another pair of corresponding sides. So the scale factor of enlargement for these two corresponding sides is the larger, W, over the smaller, 30 minus W. So by using similar triangles and similarity, we've already set up an equation with H and W in it. Now there is another way you could do it, but it's more long-winded. The way I've shown you here is the most eloquent way of doing it. The long-winded way of doing it would be to work out the area of the overall triangle, get an expression for the area of this triangle up here, get an expression for the area of this rectangle, and get an expression for the area of that little triangle, and add the three separate areas together to get the overall area. And that's another way you could get an equation with H and W. But believe me, this is more eloquent, it's quicker, it's not as time consuming. So we've now set up an equation with H and W. So we're now going to cross multiply. So we're going to end up with 40 minus H upon 30 minus W, and that's equal to WH. So multiply out our brackets. Okay, tidy up. So the WH's actually cancel, because if we bring this guy over to the other side, they wipe out. So they just wipe out. I'm going to bring the minus 40W and the minus 30H. Well, in fact, apologies, we want to make H the subject, so I'm going to bring minus 30H over to this side. So we're going to have 1200 minus 40W, and that's equal to 30H. And then we're going to divide both sides by the coefficient of H, which is 30. So divide through by 30. So we're going to have 40 minus 4/3 W, and that's equal to H. Okay, so what we've done is we've now made H the subject. We've expressed H in terms of W. So that's part A, H in terms of W. Now let's look at part B. So part B in the question says, hence show that the area of the rectangle can be expressed as this. Do you notice that the subject variable is A and the other variable is W? You'll notice there's no H. So what we're going to do first of all is set up an equation for the area of the rectangle. So the area of the rectangle is just W times H. So part B, area of rectangle is equal to WH. We're now going to get rid of H using our answer in part A. So everywhere we see H, we're replacing it with this expression, and we need to put brackets around it. So we're going to get W, and then that's upon 40 minus 4/3 W. So tidy that up. We're going to get 40W minus 4/3 W squared. And then if we compare that to what we're asked to get, you'll find that they're exactly the same. So we've now got an expression for the area of this rectangle, so as required. Part B. Okay, so part C then. It says, using calculus, find the dimensions of the rectangle which maximize the area. So remember, calculus is a fancy word for differentiation. It can also mean integration, but we've only been doing differentiation so far. So using differentiation, find the dimensions of the rectangle which maximize A. So in other words, we need to get the value of W that makes A a maximum first, and then we can get H. Okay, so remember, A is a maximum. The subject variable is a maximum or a minimum when the first derivative is equal to 0. So we're going to have to differentiate this equation and then set it equal to 0 and solve. So it's already prepared to differentiate because there's no W's on the bottom line, so we're good to go. So part C. So A is a max or min when the first derivative, so the first derivative for this equation is dA by dW, is equal to 0. So differentiate dA by dW. So differentiate the first term with respect to W. See the way W only has a power of 1, so it disappears and you're left with its coefficient. Differentiate the second term with respect to W, so we multiply the term by the power of W, so that's going to be minus 8/3 W, and then subtract 1 from the power, so it's just W to the power of 1. Okay, so we're now going to set this equal to 0. So therefore 40 minus 8/3 W is equal to 0. We're going to multiply through by 3. So we're going to get 120 minus 8W equals 0. So 120 is equal to 8W, and then divide by 8. So that's going to give us 15. So we're going to get W is equal to 15. So that is the critical value of the other variable, which makes the subject variable a maximum. We now have to prove that A is a maximum. So we're going to work out the second derivative, and we're going to sub this value of W into it, and hopefully that will show that the second derivative is less than 0. So therefore the subject variable would be a maximum. So let's see. So prove that A is a maximum or minimum. So we need the second derivative d2a by dw squared. Okay, so d2a by dw squared. So if we go back, we have to differentiate the first derivative. So there is our first derivative here. So differentiate again with respect to w. So the 40 disappears because it's just a number term. Differentiate this term with respect to w. Because w only has a power of 1, it just disappears and you're left with its coefficient, minus 8/3. So the second derivative is just minus 8/3. So there's no w left to sub the critical value into. So straight away, second derivative is less than 0. So therefore, the subject variable A is a maximum. So we're nearly there. We've worked out the critical value of w, which was 15. It's the value of w that makes A a maximum. We've also got to work out h. Remember, h is the height of a rectangle. So w is 15, we've got to get h. So we have to go back to the equation that has h and w in it. So we're going to sub the critical value of 15 into this equation. So we now need to get h. So need h. So our equation for h is h equals 40 minus 4/3 w. And we sub our value of w in, which was 15. So, tidy it up, 3 and 15 cancel, so it goes in 5 times, so we're left with 40 minus 4 times 5, which is 20. So 40 minus 20 is just going to give us 20. So the value of h is 20 centimeters. Okay, so answer, A is a maximum when W equals 15 centimeters and h is 20 centimeters. So we've just found the dimensions of the rectangle. Okay, last part, part D says, the rectangular cloth is to be dyed and this costs 15 pence per square metre. Calculate the cost of dyeing the cloth. So we're going to have to work out the area first of all in centimetres squared, and then we're going to multiply it by 15 to get the overall cost. So really straightforward. just to finish off part D. So we've worked out the dimensions, W and H. So area of rectangular cloth So area is going to be equal to W times H, 15 multiplied by 20. So that's going to give us 300 centimeters squared. Now we're going to get the cost for dyeing. Cost. So every 1 centimeter squared costs 15 pence. So 300 centimeters squared is going to be 15 multiplied by 300. So tidy it up. 15 multiplied by 300, and that's going to give us 4,500 pence. In other words, 45 pounds. Okay, if we change it into pounds, so quite expensive.